Hello everyone and welcome back to Global Technology. I'm your host, and today we are stepping back into a world that smells of hot iron and echoes with the thunder of progress. We're exploring the monumental world of heavy forging, a craft that built the very foundations of the modern United States. If you've ever marveled at the sheer scale of our bridges, our refineries, or our power plants, then you're looking at the handiwork of the forge. Today we start our journey with a deep dive into the creation of the Industrial Flange, the unsung hero of the mechanical world. Let's get close to the heat. Looking at the screen, we see the beginning of a process that hasn't changed its soul in 100 years, though the machines have grown to godlike proportions. Forging is the process of shaping metal using localized compressive forces. But to those of us who grew up in the industrial heartlands, it's much more than a definition. It's a tradition. As the video begins, notice the intense, radiant glow of the steel billet. That's not just heat, that's energy waiting to be directed. We are at a specialized facility in Dingxiang, a place famous for this exact craft. The first step you're seeing is the heating phase. The steel must reach a forging temperature, usually between 102 to 300 degrees Fahrenheit. If it's too cold, the metal resists. If it's too hot, the internal structure is ruined. It requires the intuition of a master. Now watch the upsetting process. The giant hammer comes down, and what was once a tall, cylindrical block begins to squash, getting shorter and wider. Why do we do this? It's not just for shape. When we forge a flange, we are physically moving the grain of the steel. Think of it like the grain in a piece of oak. By forging, we align that grain to follow the curve of the flange, making it exponentially stronger than a piece that was simply cut out of a flat plate. The precision here is staggering. Even with these massive tools, the tolerances are measured in millimeters. The operator uses his experience to sense the resistance of the metal. You can see the scale, that black flaky skin, blasting off the surface with every strike. That's carbon reacting with oxygen, a sign of the raw chemical transformation happening before our eyes. This first segment is a tribute to the sheer endurance of metal and the men who command it. But as impressive as these flanges are, they are only the beginning. Coming up next, we are going to witness a scale of power that makes this look like child's play. We're moving to the 3,000-ton hydraulic press to forge a massive shaft. Stay with us. If you thought the last segment was intense, prepare yourself. We are now entering the realm of the titans. We're looking at a 3,000-ton hydraulic press, a machine capable of exerting enough force to crush a mountain, yet controlled with enough delicacy to shape a masterpiece. We are about to watch a massive ingot be transformed into a high-performance shaft. This is where engineering meets destiny. Take a look at the size of that initial ingot. It's a monolithic block of steel, weighing several tons. In the history of American industry, shafts like these were the literal backbones of our greatest achievements. They powered the propellers of the great battleships and turned the turbines of the Hoover Dam. The process we're watching is called open die forging. Unlike a mold where you just pour liquid, here the metal is worked between flat dies. The operator and the manipulator driver must work in perfect harmony. The manipulator is that massive robotic arm holding the ingot. It's like a giant pair of tongs, rotating the white-hot steel just a few degrees between every squeeze of the press. Listen to the sound, or imagine it, the deep hydraulic hiss followed by the groan of the metal being forced to yield. This is cogging, or drawing out. We are increasing the length of the ingot while reducing its cross-section. Every time the press comes down, the internal structure of the steel is being crushed and refined. We are closing up any microscopic porosities, creating a dense, uniform material that can handle the torque of a massive engine. For those of you who remember the golden age of American manufacturing, this scene feels like home. It's the sound of productivity. Technical viewers will notice the reheating cycles. You see, even at this size, the metal eventually loses its plasticity as it cools. It has to go back into the furnace, the soaking pit, to bring it back to that workable orange-yellow hue. You can't rush perfection. If you forge too cold, you risk internal cracking. And on a shaft this size, a crack means a loss of tens of thousands of dollars. Watch the rounding process now. The square block is gradually becoming octagonal, then finally cylindrical. The skill required to keep the center line perfectly straight while rotating a multi-ton glowing mass is nothing short of artistic. This shaft might end up in a powerhouse or a heavy-duty industrial mill. It will spend the next 50 years spinning, carrying loads that would snap ordinary steel like a toothpick.
Bitte?
Wenn Sie möchten, kann ich Sie auch mal mit rausnehmen. Jetzt ist der Manipulator noch nicht da.
Ja.
Dann haben Sie noch mal Standort.
Das ist das Maß,
Was?
was ich eingegeben habe. Und das ist das Maß, was die Presse im Moment drückt.
Ja, ist ja bald da, ne?
Ich habe, glaube ich, schon eine Karte voll.
Ja?
Ja, da sind 2 Karten drin.
As we reach the final stages of this 18-minute marathon of power, you see the finishing tool, a flatter die, smoothing out the surface. The precision is checked with giant calipers, a nod to the old-school ways where a man's eye and a steady hand were the ultimate authority. But our exploration of heat and pressure isn't over yet. We've dealt with massive steel, but what about the exotic stuff? The alloys that don't play by the same rules. In the next part, we shrink the scale but increase the complexity as we forge non-ferrous alloys into precision bars. We've seen the heavy hitters of the steel world, but now let's change our perspective. Not everything that shines is steel. Welcome to the world of non-ferrous forging. We're working with alloys that contain no iron. Think copper, brass, or high-strength aluminum. These metals are the specialists of the industrial world, and they require a very different kind of discipline. In this video, we are observing the forging of a non-ferrous alloy into a 78mm round bar. Notice the difference immediately. The color is different, and the way the metal moves under the hammer is more fluid, almost like stiff taffy. Non-ferrous alloys are prized for their corrosion resistance and electrical conductivity, but they are temperamental. The temperature range for forging these materials is much narrower than steel. If you are off by just a few degrees, the metal can crumble or hot short. Here, we see a power hammer in action. It's faster than the hydraulic press, using rapid, repetitive blows to consolidate the grain. This 78mm bar might look simple, but its internal integrity is what allows it to be used in high-tech applications, perhaps for specialized marine hardware or electrical components that must never fail. It's a beautiful, focused process. It reminds us that whether it's a 10-ton shaft or a 78mm bar, the principles of the blacksmith remain the same. Respect the heat and control the strike. But hold on, we have one more stop on our tour. We're going from solid bars to hollow vessels. Let's look at the hot forming of tank heads. For our final demonstration, we are looking at hot forming. This is how we create the ends of pressure vessels, tanks, and boilers. If you've ever seen a large propane tank in a rural backyard, you've seen the work of a press like this. A flat, circular plate of steel is heated until it's soft. Then, it's placed over a female die. The 3,000-ton press descends with a male die, literally pushing the flat plate into a bowl shape. This is deep drawing at its most extreme. Why do we do this hot? Because trying to bend a plate of this thickness cold would create immense stress and potentially crack the metal. By forming it hot, the metal flows into the shape. These dish heads are engineered to distribute pressure evenly. In a world of high-pressure steam and chemicals, the perfect curve of these heads is the only thing standing between safety and disaster. It's a clean, satisfying end to our look at the power of the press. From flat steel to a perfect vessel head in a matter of minutes. We have traveled from the creation of massive flanges and titanic shafts to the precision of non-ferrous alloys and the shaping of pressure vessels. It is a world defined by fire, steel, and the unbreakable spirit of industrial craftsmanship. These are the processes that built our past and continue to secure our future. Thank you for joining us at Global Technology. If you appreciate the beauty of big machines and old school work, please like, subscribe, and share your stories in the comments. We'll see you at the next forge.